Count your many blessings, name them one by one, and it will surprise you what the Lord has done. Count your blessings, name them one by one. Count your blessings, see what God has done. Count your blessings, name them one by one. Count your blessings and see what God has done. Happy Wednesday. Today we're going to talk about speed, light, and smart things. It's a little bit shorter than I thought it would be considering how in-depth this particular topic is, but what do you know? Anyway, before that we're going to have a space race because, well, sort of space related. Kind of. You judge anyway. Ready? Here we go. Shout out time. Here's a shout out just for you. You support me, so I support you. This shout out is for our friends. Let's see what it is today. Hang on a minute. I missed my start button. There it is. Found it. There we go. There's She Stole. There's Cruising Nuts. There's Reef. There's We Go. There's Abundance. There's Jacob. There's Distracted. Sophie, Chris, Rowdy, Hiking Ontario, A&G, I, Wit, Northern, Traveling Van, Kaz, there's Reef. Let's see here. There's Pinned, there's Jamaican, there's Paralife, there's Yuja, Traveling Van's currently in the lead. There's George, there's Ron, there's Kifla, there's Ray, excuse me. Let's see, there's Lynch, there's Teza, there's Praying, there's Cheap. Oh, is it going to be cheap? It's going to be cheap. Alright, so Miss Cheap had posted or commented a long time ago. She's at 2K. And dollar store hauls, and we've got some giveaways. We got some crafting stuff, and then of course the playlist, no lies, but that's all right. But see, we've got hauls and we've got crafts. So if you're a crafter, you like cheap stuff, this is a good place to go. Check her out, like, share, comment, and enjoy the very advanced video for today's Wayback Wednesday. Hey, me stupid.
All right, class. Everybody sit down.
No.
Notebooks out.
No.
All right, have some fun. We hope.
Yep.
Now, most people, when they look at speed, for example, point A to point B, back in the early days of history, if you wanted to go from point A to point B, you walked. Some people would ride animals like horses. Eventually they came up with chariots and wagons, other forms of modicum of transportation. Well, for the prevailing minds, they started contemplating faster things, like, for example, gravity. Apple fell from the tree and thumped a guy in the head. It had to come at a certain rate of speed. And then at the same point, when you would try to beat the law of gravity, how fast, how far, whether in kilometers or miles, depending on what side of the ocean you're on. But for the most part, things weren't really theoretically fast until Einstein kind of turned everything on its ear in 1908, a long time ago, when he presented out what was known as the quantum theory of light. It was one of two prevailing theories of exactly what light was and how it behaved. The first was Newton's old standby called particle theory, which stated light was actually an infinite amount of particles emitted by a source. Bink! The second was wave theory, or pulse theory, which suggested that light traveled in waves, varying frequency, much like sound. Well, in 1905, during his Annus Mirabilis, Einstein found that both theories were correct, effectively creating what is now known as quantum physics. Now, Einstein's early contributions to quantum theory included his heuristic suggestion that light behaves as if it is composed of photons, and his exploration of the quantum structure of the mechanical energies of particles embedded in matter. By 1909, he introduced what was later called the wave-particle duality, the idea that a wave theory of light has to be supplemented by an equally valid yet contradictory quantum theory of light as discrete particles. Now, many of Einstein's quantum ideas were incorporated into a new model of the atom developed by the Danish physicist Niels Bohr in the first decades of the century. Bohr explained that electrons occupy only certain well-defined orbits around a dense nucleus of protons and neutrons. He showed that by absorbing a discrete quantum of energy, an electron can jump from one orbit to another. Now, along comes 1916, Einstein found that he could explain Max Planck's black-body spectrum in terms of an interaction of photons with the new Bohr atoms. However, his arguments for light quanta were well-founded. The physics community did not take them seriously until 1923. Why would we want to, listen to this upstart? Well, in that year, American physicist Arthur Compton measured the transfer of momentum from photons to electrons as they collide and scatter, an observation that made sense only in terms of the particle nature of light. Now, in spite of this contribution of the Bohr model to the atom, Einstein remained deeply troubled by the notion that atoms seem to emit photons at random when their electrons change orbits. He considered this element of chance to be a major weakness in the model, but he hoped that it would soon be resolved when the quantum theory was fully developed. However, by 1926, the problem of chance remained, and Einstein became increasingly alienated from the developments in quantum theory. He insisted that God does not play dice, and thus there is no room for fundamental randomness in physical theory. This is man we're talking about. Everything's random.
Random! Spin the wheel.
Yeah. Now, in November of 1922, when Einstein and Elsa were visiting Japan as part of an extended tour of the Far East, they received the news that Einstein had been awarded the 1921 Nobel Prize in Physics. Now, although Einstein was most famous for his theory of relativity, the prize was officially awarded for his work in quantum theory. Throughout the first quarter of the century, Einstein made many important contributions to this field. The first was the 1905 paper on the photoelectric effect. From 1905 to 1923, he was one of the only scientists to take the existence of light quanta, or photons, seriously. However, he was strongly opposed to the new version of quantum mechanics developed by Werner Heisenberg and Erwin Schrödinger in 1925 and 26.
How scandalous.
How scandalous. In 1926 onwards, Einstein actually led the opposition to quantum mechanics. He was thus both a major contributor and a major critic of quantum theory. Well, that year, 1926, was a critical turning point of the quantum theory because it witnessed the emergence of two new forms of quantum mechanics. The first, wave mechanics, was a mathematically accessible theory based on Louis de Bragel's idea that matter can behave as waves, just like electromagnetic waves can behave as particles. The idea received the strongest support from Einstein, Planck, de Broglie, and the Austrian physicist Erwin Schrödinger. The opposing camp, which was led by the German physicists Max Born, and Werner Heisenberg, as well as the American Paul Dirac, formulated that the theory of matrix mechanics was far more mathematically abstract and involved the elements of chance and uncertainty that Einstein found so philosophically troubling, basically chaos theory. Well, 1928, 2 years later, Heisenberg, Bohr, and Born developed the Copenhagen interpretation, which joined the matrix and wave mechanical formulations into one theory. This Copenhagen interpretation relies on Bohr's complementary principle, the idea that nature encompasses fundamental dualities and observers must choose one side over another in making observations. The interpretation is also based on Heisenberg's uncertainty relations, which state that certain basic properties of the subject, such as the position and momentum of the subatomic particle, cannot be measured simultaneously with total accuracy. Thus, the Copenhagen interpretation explained that while quantum mechanics provide rules for calculating probabilities, it cannot provide us with exact measurements. Well, I can understand why Einstein was against this. Now, following these new interpretations, Born and Heisenberg proclaimed that the quantum revolution had come to an end. Quanta were a mere means of calculating probabilities, but did not account for the phenomena in which they actually occur. However, Einstein could not accept the probabilistic theory as the final word. As he saw it, the very goal of physics was at stake. He yearned to produce a complete, casual, deterministic description of nature. In an ongoing debate with Bohr that started at the Solvay conferences in 1927 and 1930, it lasted until the end of his life, Einstein raised a series of objections to quantum mechanics. He tried to develop thought experiments whereby Heisenberg's uncertainty principle might be violated, but each time Bohr found loopholes in Einstein's reasoning. In 1930, Einstein argued that quantum mechanics as a whole was inadequate as a final theory of the cosmos, whereas he was once regarded as too radical in his quantum theories, he now appeared to be too conservative in the defense of classic Newtonian ideas. In the 3 decades prior to his death, Einstein's distrust of the quantum theory isolated him from the mainstream developments in physics. All of his greatest contributions in science had been made in 1926, and from this point on, he remained a staunch opponent of the theory he had done so much work to build in his earlier years. Einstein focused his efforts instead on developing unified field theory, a theory which would explain both gravity and electromagnetism in one principled mathematical account. He hoped to resolve the conflict between the smooth continuum of space-time, described by the general theory of relativity, and the jittery submicroscopic particle world where quantum theory reigns. Although he never succeeded in this endeavor, in a sense he was simply ahead of his time. Throughout the 1980s and 1990s, the primary goal of theoretical physicists was the formulation of a grand theory of anything, or TOE, which would account for every element in the physical reality. Now, the thing that makes it kind of interesting, again, talking about a guy who was putting together these theories in 1908, one of the first things that he was trying to lock down was the theory that the speed of light is a constant. It will only go so fast, it cannot go beyond the speed limit. And of course, man and us are wanting to go as fast as possible. They have started to come up with ideas on whether certain reactions in space, you can have what's known as curved space occur. You can have cases where the big thing that a lot of people try to use as a constant is the theory of the light year. For example, they say that light can travel at a certain given speed. Thusly, they can put a prediction out there that says, okay, this galaxy, we'll use the nearby Andromeda galaxy as a good point of view, even if it's 300 light years away, well, 300 years ago, the light is just now getting to Earth. Well, that means Andromeda is in the past. Well, by that standard, we might not even know if the Andromeda galaxy is still there or not. All we know is eventually it's going to run into the Milky Way galaxy if it continues on its normal course of action. But at the same time, there's questions on if you have a galaxy or if you have a source of light, take a view of the outside world with all the millions of stars you can see, and then say something between that star there and the Earth happens. You could have a nearby black hole. You could have a solar system that might come through the area, another galaxy. You might have a comet go through. Is light going to be unaffected by, a system of events going through? Wormholes. There's a lot of questions that, are still being asked out there, which is really kind of what's fun about our scientific community that we're dealing with right now. And I know just recently that they were talking about the fact that, there's the matter, antimatter, or the fact that eventually they hope to harness the ability to use light as a form of travel, for all you Star Trek fans out there. Because eventually, they want to be able to go, to warp drives and stuff like that. Because right now, I'm trying to remember, I think the nearest star that we have, Alpha Centauri, they said basically it would be, even at the speed of light, it would take X number 100 years to get there. So basically, if you loaded the ship with 100 humans, 50 men, 50 women, and then over the course of the 200 years it would take to get to the nearby star, anybody who left Earth would not survive. They would die off. Another generation would have to basically grow up in space.
Wally!
Oh, yeah. The only problem that they also have with that, for those of you who've been following the recent missions where they had a couple astronauts get stranded, space is not very friendly to human beings. Your body chemistry has issues. Your bone density starts to break down. It's not something, if you're not used to it. I mean, when they had the space lab, Skylab was up in the atmosphere, and of course we still have the ISS out there. They would have the astronauts try to exercise, to stay in shape, to keep their muscle tone, and even they were fighting against the clock. It's just one of those fun things. But now that we're looking at both the science of light speed, the distances, and the different variations that they've been dealing with, it'll be interesting to see what the next generation of scientists are going to come up with for the light speed theorem, because some of the most recent things that they've come up with, when they tried to use that new James Webb satellite to look back to where the Big Bang supposedly originated from, they discovered not all of these galaxies and solar systems could have come from the Big Bang, because their speeds are all different. They're not all traveling at the same rate of speed. And then from there, it's also the same, call it the three-dimensional probability issue, is that if the Big Bang happened in this one location in space, and the Big Bang went off, did everything just come out in this degree of direction? Or was it all-encompassing, and when the Big Bang happened, the cloud, for the best word you can describe of it, everything just flew out in different directions.
Fly!
Whee! And so, it comes down to the grand question. And then, some of these galaxies, when they flew off in their random course of action, what gave them that individual push? All random? Complete chance? Galaxies do collide with each other, and it can be quite spectacular at times. But at the same time, you also have things that are going on out there that there's just not been a lot of research able to be done. Fun things like neutron stars, black holes, quasars. I was reading earlier that they were talking about one case where they had a neutron star. They say that if you could get the hold of a piece of a neutron star, this is kind of scary, 1 inch by 1 inch. Got to take your rulers, figure that out. A 1 inch by 1 inch square of neutron matter would weigh more than all the vehicles in North America. That is dense. Can't imagine what that'd be like slamming into the earth. But, as they take this problem and start experimenting with it more, it's also kind of interesting that he came up with this back in 1908, and you think about all the things that we have done since then regarding both going faster and quicker, and we had to come up with, well, let's start with it, automobiles, the railroad, aircraft. Eventually, when we decided that Earth wasn't big enough for everybody, we invented rocket flight to get not only off the planet, but eventually we were able to settle on the moon. And then there's my personal favorite, when they launched the 2 Voyager probes. And right now they have actually left our solar system. And it's kind of wild, 19,000 some miles per hour, and we haven't even gotten to like 1% of what light speed is. But we do know that when you get beyond the Earth's gravity and you just get that little thrust, you don't have to keep the motors running. It'll just, you're basically like the ultimate putt. You're going until you run into something. For good or for bad, that's where Voyager is going. So if they ever figure out a way to use light as a propulsion system, that will open up all sorts of new doors as far as interstellar travel. Of course, by that time, the aliens might say we're a danger and a threat to everybody else and decide to blip the Earth.
The only people that humans are a danger to are themselves.
That's probably why they're not contacting us. They said, these guys will destroy themselves, we'll let them do that. Just don't let them off the Earth. They can send out their unmanned probes, that's fine. Those are not harmful. Of course, the ones out there with radioactive material on us, don't worry about that. It's how they, power source, but yeah.
Nobody wants to talk about those.
No.
Those do not exist. What are you talking about?
No, we're perfectly safe here. But anyway, this has been a shorty for the Bud Files, for the Bearded Historian. But we'll catch you guys next week, and you guys have a good day. Bye-bye.
I thought that would have been